So we know all of this from our grade 12, so that's going to benefit us to knowing what the answers are already, because we can find them using the rules and stuff from our grade 12 course with the non-permissible values. So, but we're going to use limits to do that as well. That's our goal today. So you have to use limits in this lesson to figure out your asymptotes. Like I've already tested, Rahat, you said one more reel. It can't be that long. The reels aren't that long. So to figure out our vertical asymptotes, it's going to be if our limit is approaching infinity. And it can be from either side. It doesn't have to be, like as long as it's infinity positive or infinity negative, it's considered an asymptote. So the first thing you're going to do is you're going to find your MPVs, and that will be what x is approaching in the limit, okay? And then step 2, you're going to simplify your equation, and then you're going to evaluate your limit for each NPV. If the limit approaches infinity, it's an asymptote. If the limit approaches a number, like it approaches 0 or 1, it's a POD. And then give the equation of the vertical asymptote in the form x equals. So this is a way without graphing to know how to do it. So, sorry? No, we're good? Okay.
Like, what if the limit does not exist? Like, it's still an asymptote, right?
It's still an asymptote. The limit may not exist, but if we're going to be looking at it from, if it's like this, it's still an asymptote. We're looking at, does that asymptote exist? So we're going back to looking at the x's for a minute, but by using what the y's are doing. Okay, so let's look at this one down here. Okay, so step 1 was to find our NPVs. So our NPVs are what? -3. So we're going to be assessing the function. So the limit, and this only has one NPV. Right, so we're using that NPV as what the x is approaching. And then step 2 is to simplify the function. This one actually doesn't simplify. I mean, I can factor it, excuse me, but it doesn't simplify. So if I were to do a direct substitution in here, what would I get? Right, so if we do direct substitution, we're going to have 2 times, sorry. So that's the undefined. That's not indeterminate. Why are you getting your phone out? I don't understand. I don't understand. Oh, what's happening? Look, Rahat, you've upset my computer so that it won't do it. Okay, so direct substitution isn't going to work, so this ties into yesterday's lesson. So if direct substitution doesn't work, what we're going to have to do is we're going to have to look at it from the left-hand side and the right-hand side. So if we look at the limit as x approaches -3 from the left, so what's a value left? What's a really, really small increment away from -3 but to the left?
-3.001.
Sure. So when we're looking at the left-hand side, we're looking at those small, tiny increments. So we're going to do the ish math that we talked about yesterday. So we know that if we put, if we use -3.001, we know that the top is going to be approximately -8, and the bottom is going to be, it's going to be a very small negative number, right? Everybody agree with that? So if we do that math there, where are we headed to? We have a negative on top, and we have a very, very small negative on bottom.
Positive, not negative.
We're headed to positive infinity. right? So that's that ish math from yesterday. And then we're going to go to -3 from the right-hand side. So what kind of number would be to the right of -3? So maybe -2.99. So again, on the top, it's going to give us approximately -8. And then on the bottom, it's going to give us small positive. So if it's a -8 divided by a small positive number, where am I headed to? Negative infinity. Okay, so we would say that the limit does not exist at -3 because one's going to positive infinity, one's going to negative infinity. The limit doesn't exist, but because these are headed to infinity, we know it's an asymptote, not a POD. Are we good with that? That makes sense, sort of, kind of? So we're using limits to prove that it's an asymptote. Now, you all just trusted me in grade 12 that an asymptote actually existed where the non-permissible value is. And in most cases, that is true, but sometimes the functions get more complicated. We have diagonal asymptotes and things like that. So things get complicated quickly, or can get complicated quickly with bigger ones. Okay. So now we're going to do this one. So if you do direct substitution, so you have something like that, and that's just weird. And so in math, we would say that that's undefined because infinity would include all numbers, which would include 0 as well. So we say that this is undefined. It's not indeterminate, it's undefined. So if I do my direct substitution, I have a problem here. So if it's undefined, I'm going to use my left and right hand side again. Where would my non-permissible value be of this function?
X not equals
0, right? So when we're looking at what values to put in our table, we're looking at things around 0. So, and you can use ish math as well if you wanted to. But 0 would be that undefined because of our non-permissible value. So if we were to pick values less than 0,
Why are we picking 0? We can pick infinity or pick
right, but what's the non-permissible value for this function? 0. So we know the thing, whether it's a POD or an asymptote, is going to be at 0 because it's related to our non-permissible values. So we're looking at...
to see X approaches infinity. It's an extra part.
Yeah, it's kind of an extra part to it. It's like we're looking at the non-permissible value, and then we just kind of have to figure out what's going on. And we know what's going to happen here, I think. I think we know what's going to happen. So if I do to the left-hand side, let's say -1. Oh, no, we can do -10. We're going to infinity, right? So 1, 10 here. Ooh, sorry, that's -1. I was doing the other one.
Do you get a B?
No.
No, so like...
Okay. this is what I should tell you, and this is what I didn't tell you. When we're looking at limits to infinity, we're looking at horizontal asymptotes. So if we look at these, numbers, we know that we're getting, like if we go this way, where are we headed to? We're at -1, we're at -0.1. Where are we going? We're going to 0. If we go this way, where are we going? We're headed to 0 here. We're headed to 0 here. So that means I have a horizontal asymptote at y equals 0. Now remember, we had the 3 rules that we had to use. So we have a asymptote here. Sorry, that's really hard to see on mine. It just looks like I'm drawing a darker line. So this, anytime we're doing x to infinity, it's dealing with our horizontal asymptotes. So that's why, and so if we then look at where's the vertical asymptote, we got to re-look at this question, but this time we're looking at where x approaches 0. So this with the infinity is for our horizontal asymptote. This to the non-permissible value is our vertical asymptotes. So again, if we do direct substitution into this one, we are going to find that it's not going to work. It's going to be undefined. So if we pick values left of 0, so if we're doing the limit as x approaches 0 from the left, that's going to be 1 over a small negative number. So that's going to be negative infinity. And then if we do limits as x approaches 0 to the right, so that's positive, so we know that there is a horizontal asymptote happening, or sorry, a vertical asymptote happening here. And we could graph it, but we don't need to. So this would mean my vertical asymptote at x equals 0. Okay, that was really messy writing on my behalf. That wasn't very good. That was terribly messy. I apologize. So when you're doing limits to infinity, you're looking at, what are you doing? You're looking at vertical asymptotes. Okay, but you just found a known truth in math, and what we know is that the limit as x approaches infinity to 1 over x is equal to 0. That we know to be true. You do not have to prove this time and time again. It's known to be true. So you don't need to prove it, you just need to know it.
We don't need to prove, right? Because it says
Oh, sorry. Do not need to prove. Thank you for correcting me. All right. So some basic limit stuff. Some basic limit stuff is going to be that if you have a constant, like if we use our log theorems, and this would be the limit as x approaches infinity of k times 1 over x. We always want to use that 1 over x because we know its value. We know what it is already. So we can actually pull that k out. That was the constant theorem from L2. So this would be k times the limit as x approaches infinity of 1 over x. And we know that has a value of 0. It's equal to 0. So it would be k multiplied by 0, which is just 0. So if you have a function that is 2 over x, you don't have to do any math. You already know the limit's 0. All right, so the power theorem also states that we can write it this way. Actually, there should be big brackets around it. We know that this has a value of 0. 0 to the exponent of anything
1.
is going to be 0. Anything to the exponent of 0 is 1, but 0 to the exponent of anything is 0. What's 0 to the exponent? 2. 0 times 0. You got it backwards. That's okay.
What would happen if it's 0 raised to power 0?
Oh, we're not going to talk about that. I feel like the world will collapse on itself, and we just probably, it's just, whoa, that's a lot.
Yeah, E.
Yeah, you just get an E error. So those are some really simple rule limits. So if you have that, if you can always get that 1 over x in there, you know that your function, your limit, is 0. Okay. So here we go. If we are doing x to infinity, we're looking at vertical asymptotes. Okay. So if we substitute in here, if we do direct substitution in here, it's going to be 2, 7 times infinity minus 5. We know that infinity could be any number, right? So we know that this is going to go to undefined. You do not have to show this every time. I'm just, direct substitution won't work here. All right, so we're going to do some math, and we're going to put in that 1 over x. Okay, so what we're going to do, because we got to do some math to make this work. We can't just say, no, it doesn't work. I'm going to times the numerator by 1 over x, and I'm going to times the denominator by 1 over x. And the reason why I'm doing 1 over x is because we know the limit x approaching infinity to 1 over x is 0. So that's going to be always kind of like the thing I'm going to use. So if we multiply that through, oops. Are you guys okay that I broke those two terms up on the bottom? You guys are okay with that? Okay. These are going to end up canceling each other out. And that's about all I can do there. But now I can use my limit theorems and break this down. So this is where those limit theorems come in, where things don't work. So we can take the limit as x approaches infinity of 2 over x, divide it by the limit as x approaches infinity of 7 minus the limit as x approaches infinity of 5 over x. So now we know some things. What do we know? What's this limit equal to? 0. What's this limit equal to? 0. So we're going to have 0 over 7 minus 0, because if we take, there's no x in here, so it's just the limit is 7, because that's the function. And so that's going to equal 0. So the limit of this function is 0. So we are going to have a horizontal asymptote at y equals 0. Okay, here we go. Now, if we sub in the infinity, it's going to be infinity over infinity, right? So it's going to be that undefined again. There's nothing we can really do here. So we're going to apply the same strategy, but this time, because remember that 1 over anything to the power of x is still 0. What's our highest degree in this one? 2. So this time we're timesing the numerator and the denominator by 1 over x squared. And the reason why I picked that was because of the highest degree, they match, right? And we know that it still has a value of 0. So we're just using that to do some math to get this to work. Hey, if we were to, sorry, I'm just going to slide back up to this one. If we were to use our rules from grade 12 and just look at that function, would we have an asymptote at 0? Yeah. Memorizing the rules is a little bit nicer. But the rules there's a little bit of a lie in the rules that I gave you. When the degree of the numerator is greater than the degree of the denominator, we said that there was no asymptote. That's not really true. It's actually an asymptote equal to the coefficients, and it usually ends up being a diagonal line. So I kind of lied to you. I'm sorry, but only you guys know that. Nobody else needs to know.
All the rules are right from this, like what we are doing.
Mm-hmm. Yes. Yeah, and we give it to you in a little easier form, and we don't really go ahead and derive them, but they're here. They're all in calculus.
This is the moment from grade 10, right?
It's the moment from grade 10?
Right, like when all the calculus, the pinnacle.
It's the pinnacle. Absolutely it is. So we are going to have the limit as x approaches infinity to 2 plus the limit as x approaches infinity to 3 over x minus the limit as x approaches infinity to 4 over x squared. Oops, all over I'm writing really crooked. The limit. So unfortunately, I won't accept the rules anymore. You've got to be able to do it mathematically now. You got to do it with limits now. And so what do we know here? We know this will have a value of 0. This one will have a value of 0. This one will have a value of 0. This one will have a value of 0. So what's left? 2 over 5, which is our rule. When the degrees are equal, we take the leading coefficients. But it's all based off limits, but just we didn't have enough knowledge at that time to do that.
That would have been too much.
Too much for our little brains. We spent a lot of time looking at x's, and calculus really takes its time looking at the y's. Okay.
I guess calculus already got rejected, so now.
Ouch, nobody. Okay. Am I okay to flip? I think I already covered this. So when we're looking for horizontal asymptotes, we know that that happens when we're looking for x approaching infinity. That's going to give us our horizontal asymptote. If it's approaching, sorry, I only highlighted one of them. Any asymptote. It could be negative asymptote, or it could be negative infinity, could be positive infinity. Non-permissible values is going to be your vertical asymptotes. And the horizontal line y equals k is a horizontal asymptote if one or both of the following is true. Do you guys know what y equals k is? That would be a constant, right? K in math is like, so 3 or 4 or negative 16. So we know that if the function is equal to a constant, that's going to be your horizontal asymptote. So approaching infinity, we know that we're looking for our asymptote. If it's equal to a constant, that is our asymptote. Didn't we just do this one? I feel like this was our first example. Oh, this wasn't our first example. Nope, not even close. Not even close. Yep, no, it's the exact one. It's example 2. I think we're good. We don't need to do that one again. It's like, why is that there? Okay. Some things you need to pay attention to. It's possible, but it's unusual for a function to have more than one horizontal asymptote. It will happen if you're looking at negative infinity, it's approaching a value, and then you're looking at positive infinity, and it's approaching a different value. So we could actually have 2 horizontal asymptotes. It doesn't really happen that much, but the inverse of the tan graph, like this is a tan graph, kind of the x's and the y's have been flipped. So we would find in that case that there is 2 asymptotes on that one. Okay, well, I think we just did this one too. All right, well, this is a fun lesson. Okay, good job, everybody. We know the asymptotes at 2/3. So just some quick notes. You use x to the infinity, and you use the known truths that the limit of x approaching infinity of the function 1 over x is equal to 0. And the other one is, as the limit as x approaches infinity, what's the other one? Xn is equal to 0. And we're going to use that xn, x to the exponent n, when we, like if they were degrees of 3s, we replace that with a cubed function. So simplify the aversion, it's not going to work. Multiply the appropriate known truths, simplify and evaluate, and state the equation of the asymptote in y equals form. And that's it. That's all. Easy peasy. So that's where your limit theorems come in.